Hello everybody and welcome to exercise 1E on page 107 of the workbook. And this exercise has its instructions back a couple of pages, so let's remind ourselves of what those were again. They're giving us a matrix and asking us, is this a diagonalizable matrix? And if it is, to find those special matrices Q and D that we've been talking about. Okay, well, the key to determining diagonalizability is to find eigenvalues and eigenvectors. So we'll start out by doing that. Okay, so to find our eigenvalues, we need the determinant of this matrix. Okay, and by now you may be getting sick of watching me take determinants and calculate eigenvalues and eigenvectors. So if that's the case, feel free to fast forward here over this part of the video. Okay, so we're going to take that determinant. Notice that we've got some zeros in the first row, so that's probably where we want to expand along. So we're going to get 3 minus lambda times the determinant of the 2 by 2 that looks like negative 1 minus lambda, negative 1, 4, 3 minus lambda. Okay, and continuing with the algebra here, we're going to get 3 minus lambda and then the determinant of that 2 by 2. Okay, if we write out the steps, looks like that. Minus a negative 4 is a plus 4. Okay, and I'm trusting that you can kind of do the algebra that's in the brackets there. And if you do that, you're going to get, let's see, 3 minus lambda. That part in the brackets is going to reduce down to lambda squared minus 2 lambda plus 1. Okay, and if you factor that one more time, pull out a negative sign, and here's what you're going to end up with. Okay, that lambda squared minus 2 lambda plus 1 factors is lambda minus 1 squared. Okay, so if you set that equal to 0, we're going to get two solutions, so two eigenvalues. And let's start with, I'm just going to pick the lambda equals 1 eigenvalue as a starting point. All right, so if we go back to our matrix up here, A minus lambda I, and plug that in, we're going to get, let's see, 2, 0, 0 in the first row, then 7, negative 2, negative 1, okay, and negative 8, 4, 2. Okay, and if you reduce this down, you can either do this by hand or by calculator. Here's the matrix that you're going to end up with. Okay, so how many pivot positions do we have? Okay, well, it looks like we've got 2, which means that we're going to have one free variable. So if we map all of that out, looks like x3 is going to be, we'll let x3 be t because that's our free variable. And if you solve for x1 and x2, you can confirm my calculations here. You should get x2 equals negative 1/2 t. Okay, and x1 equals 0. Okay, so what would a basis for our eigenspace look like then? Right, well, we really just need we really only have one eigenvector here. We can choose t to be anything we want as long as it's not 0. Here a convenient choice would be 2 maybe, because it's going to knock out that 1 over 2. Okay, and so if we do that, let t equal 2, we're going to get 0, negative 1, and 2. Okay, there's a basis for our eigenspace. Okay, now the next step would normally be to go ahead and look at our other eigenvalue, lambda equals 3, and kind of continue this process. But hold on a minute here. We may be able to save ourselves some work if we think about this. Okay, so what was the multiplicity of this eigenvalue, lambda equals 1? Okay, the multiplicity was 2. And how many eigenvectors were we able to find? Just 1. Okay, so if you look back at the theorems on page 104, we already know that this matrix is not diagonalizable without doing any work. because it said to have any chance of being diagonalizable, we need the number of eigenvectors to always match the multiplicity, and we see that it doesn't. We don't have enough eigenvectors to go with this one eigenvalue. So we are actually done with the problem at this point if we make that observation. Okay, all we have to say is really this. Since the dimension of our eigenspace is just 1, okay, because we've just got one vector in our basis, and that's less than 2, the multiplicity, we know that A is not diagonalizable.